Hello, today we're talking about graph analysis. And graph analysis is using calculus to analyze a curve or to look at a curve and determine what we know about it, or look at a function to determine what we know about its graph. So first thing, we're just going to start with some basic vocabulary. We're starting with a positive function. So a positive function is a function, I'm trying to write here. Hold on. Sorry, is a function with positive y values in the, so it's in the first and second quadrant. Function with positive y values. That also would mean that the graph is in the first and the second quadrants. The diagram, any kind of a sketch where everything is positive is good. Okay. And how is it found? Graphically, it's got to be above the x-axis. And another way to do it, we can just plug in an x value. And to get the y values. Or we can look at the function and know, for example, x squared is always going to be a positive function. So a negative function, you should be able to write the definition diagram and how is it found for negative function. So I'm going to ask that you pause the video now and do the negative function. So go ahead and take a look at your negative function, what you wrote and what I have, and pause the video to go ahead and fix what you have. Increasing, so technically how we think about it is as x gets bigger, so does y. If we were to sketch a graph of an increasing function, it's just something that's going up all the time. But let's put this in terms of calculus. And in terms of calculus, what this is the slope of the tangent line is positive. So when we look at the graph that I have, if you were to sketch little tangent lines, all of those little tangent lines would have a positive slope. That means that that function is increasing. For what we can see, that function is increasing. So the slope of the tangent line is positive. That translates into the derivative. So where it says how is it found, we want to find where the derivative, because that's the slope of the tangent line, is positive. So at this point, I would like for you to do the decreasing. So go ahead, pause the video, and complete the row for decreasing. So here is the decreasing information. Might want to go ahead and pause the video and make sure you have that all down. Concave up. I'm going to start concave up with a sketch of what it looks like. And what it looks like is a function that kind of looks like a parabola or a bowl. The concavity, this is called concave up. So for what it actually means, or its definition, it's that if we were to put in the tangent lines, and I'm going to quickly put the tangent lines in and then take them out, this tangent line has a negative slope, has a negative slope, negative slope, negative slope, negative slope, zero slope, and then my tangent lines change so that they have a positive slope. So the tangent line slopes change from negative to positive. Okay, so the tangent line slopes change from negative to positive. That means we have a concave up figure. And how we're actually going to find that is, it actually is my second derivative. And that's going to be where my second derivative is positive. So what I'm asking you to do now is do the concave down row. So pause the video and complete the row for concave down. So here is the concave down row. So pause the video and fill in anything that you need to fill in. The absolute or global maximum. The absolute and global, those words will be used interchangeably. And what that means is literally the biggest Y value and that also means it's the highest point on a graph, the highest place on the graph. So if we had a sketch of a function, and in this case, the absolute maximum would be where that dot is. So I'm just going to write max, even though that's an absolute maximum. Okay, that is the highest thing. So the next column is now available to us, and the question is, well, what is it? And the absolute maximum is a Y value. Okay, it's not a point, it's not an X value, it is a Y value. If the question says, where is the absolute maximum? That would be an X value. If a question says, what is the absolute maximum? That's going to be a Y value. So there's a couple ways we can find it. Graphically, we can find the highest Y value. And we can do that in our calculator. If we have our graphing calculator, we can just find a maximum. The other way that we can do this is by setting the first derivative equal to a value. And in this case, when we have a maximum, I'm going to draw in a little tangent line at my maximum. What is the slope of that line? And the slope of that line is 0. So it's going to be where my first derivative is 0 is where I'm going to check for my maximum. So it's not only where my first derivative is 0. I'm going to draw in another tangent line on my graph because right here I also have a tangent line where the derivative is 0. So we've got to find where the first derivative is 0, then find the highest Y value, or find the biggest Y value from the places where the first derivative is equal to 0. So what I'd like you to do now is the next row, which is the absolute or global minimum. So go ahead and complete that row after you pause the video. So here's the absolute or global minimum row. So pause the video to complete that one. Next is the local or relative maximum. And again, I can say a local maximum or I can say relative maximum. Those words are interchangeable. So the local maximum is any high point or any low point. So when you go back to the absolute global max, I've circled it in green, you see I have two tangent lines at the peaks in my graph. So the local or relative maximum is going to be any one of those peaks. So I don't know how you want to say that, but I would just say it's a peak on a graph. Now I'm going to write down in the bottom what it actually means in terms of a derivative. If you look at a peak, then we have concavity here, and I'm going to put a little box around what I'm talking about. The concavity of this is it's concave down, and we know that this is concave down because the tangent lines are changing from having a positive slope to a negative slope. So in terms of that, another definition for a local max is where f changes from increasing to decreasing. So it's literally where my function starts going up and then reaches a peak and then starts going down. So my function is increasing at first and then it becomes decreasing. And the other thing that we could say, because we know it's changing from increasing to decreasing, it is where f prime, the derivative, changes. Well, when my function is increasing, my derivative is positive, so it changes from positive to decreasing, where my function is decreasing, my derivative is negative. And that's called the first derivative test. So again, a sketch. It's just going to be any of the peaks that we have. So all of these are called local maxes. All of them. So here, here, here. And again, a local relative max is still a y value. And how we're going to find it is we're going to first take the first derivative and set that equal to 0, because that's going to be either a maximum or a minimum. And then we're going to use the first derivative test. And when I say the first derivative test, we want to look for f prime changing from positive to negative. Now, I mentioned concavity. So concavity, we've already discussed. If I've got a local max, then my function is concave down. And when you look at concave down, what I know is the second derivative is negative. So I can also use the second derivative test. So I can do the first derivative is equal to 0. Then the second derivative test. And that is where my second derivative will be negative, because that means my function is concave down. So if I know my derivative is 0, that tells me that I have a tangent line of 0. And if I also know that my second derivative is negative, that tells me that my function's concave down, which means I have to have a scenario where I have a local maximum. So at this point, go ahead and shift your paper to the back of this page, and go ahead, and I'd like you to pause the video and complete the row for the local minimum. Go ahead and pause the video now, please. So here is the local minimum row. So go ahead and pause the video and complete that if you need to. The next item is extrema. And the extrema are just all of these local mins and maxes. So all local minimums and local maximums. So if we have a function, it's any peak, it's any valley, it's anything. So these are all extrema. And again, extrema are still y values. And we find them by finding either, my extrema can be at endpoints, and that's a point that I need to reiterate. Any global maximum, any global minimum, any local minimum, any local maximum could be at an end point. So we are going to have to check our end points as well as using our first derivative and second derivative tests. So we need to check for endpoints or critical points. Well, what are critical points, you ask? That's a good question. Let's look at what a critical point is. A critical point is a point where my first derivative is equal to 0. Or my first derivative is undefined. Now, a critical point must be a point on the function. So it's got to be a place where the function exists, but the derivative is undefined. So, and again, that would be pretty much your extrema or an undefined point. So this, I'm saying this is where my function, my derivative is undefined at that sort of middle point where I cross the x-axis. Now the difference between a critical point and everything else we've done is it's actually a point. So a critical point is an x and a y value. Now the way we find that is we take the first derivative and set it equal to 0, or we find where the first derivative is undefined. Lastly, we have a point of inflection. A point of inflection is a place where a function changes concavity. And again, it's a point. So where a function changes concavity is where it changes from concave up to concave down, or from concave down to concave up. So in this picture right here, I'm estimating the point of inflection to be about right there, where my function is changing from concave down to concave up. And again, what is this thing? It's a point. So it's an x comma y. And how do I actually find where my point of inflection is? This is where my second derivative is equal to 0. And we have two things. We've got to have both. And my second derivative changes sign, which means my second derivative changes from positive to negative, or my second derivative changes from negative to positive. So because my concavity is based on my second derivative, where my function is concave down, my second derivative is negative. Where my function is concave up, my second derivative is positive. So in the example that I have drawn, I should be able to set my second derivative equal to 0 to find the x value. Then I need to determine that before this x value, my second derivative is negative, because it's concave down. And then after that x value, my second derivative is positive. And we do that simply by substituting values into the function. So at this point, what I'm going to suggest is that I'm not going to do it. We were going to go over it in class. I would like for you to do questions 2 through 8. So I don't want you to do example 3, but I think at this point you should be able to do questions 2 through 8 before coming to class. So go ahead and work on that before you go to bed tonight, and I will see you to talk about everything else that's in this packet. So have a wonderful evening.